going live. Right. So yeah. So this video is the NSIGII command and control on the fly read read, write, and execute verification. Um, yeah. So terminology. NSIGII, the world's first human rights protocol. I mean, gambling hopefully goes viral. Anyway, um, N for November, S for Sarah, I for Indigo, G for golf, I for India. World's first human rights opposition week OS, M for Mike, U for November, K for Kilo, O for Oscar, dash O for Oscar, dash S for Sarah. Human rights protocol. Command and control, as in control and command. This is just controlling stuff and commanding stuff. SIGI is a scripting system, but it's basically scripting that removes protocol. So SIGI verifies the paperwork. They give you houses, but it gives you houses where you need houses, not where you want houses. So it's basically this is scripting. Think of a SIGI S for November, S for Sarah, E for Echo, F for France. The SIGI special files as expressing intent, which gives the intent files. But there's a trial interpretation. Do I want house? Do I need house? Do I want a house? Do I need a house? Do I want a house? A question of ambiguity. Do I want or need? Could I, instead of the system of asking for houses, so do I want a house? Yes or no? Do I need a house? Yes or no? And there may be one, should I get a house? Yes or no? These questions are what consensus mission is based on via the principle of the SIGI on the fly verification. Because these questions are resolved in time, ahead of time. So if I give you a 1, you give me a 0, but do we have a consensus in the middle? Well, we can always agree on that we need as a foundation. That's what SIGI Verify is doing. It's verifying, do I need a house? Do I want a house? Should I buy a house? These two questions consent to yes, no, and maybe. Yes, no, and maybe. No, it's a question answer system, but it's a simple question for the foundation via principle, the dimension of principles, the principles of dimensions of the questions, and shared heuristic problems to solve via repair and renew, build and break, and create and destroy. NSIGI is a human verification. These automate stuff. It's a good system, but it's a good system, yes. But it's to allow you to. Let's say NSIGI is an on-the-fly scripting system. It's a scripting system that allows you to automate the things you never need to do, like paperwork, to issue someone housing, like me. But that's good. It's a scripting system. I should tell you, it's a scripting system that runs scripts and holds it in memory and needs to change. Holds space for allocation for things that needed, not wanted. Before you can get the want, you can get the need. The need is stable. And it's basically based on the principles of dimensions that all dimensions share, left, right, up, down, or center. Whether the center may lie, whether we agree with the center based on the rules defined in the framework of rigidity, in the framework of consensus. Non-rigid flexible polar consensus, that is. To give you structure or syntax. What is the meaning of love? What is the meaning of hate? What's the meaning of theological system? So let's get started. So, what can you see on my board? The board has 3 systems: read, write, execute. And I'm making a read, write, execution table here via the framework of read, R for read, and W for write, and execute. This is a Cisco order model of the system verification. Cisco works here and verify. So Cisco means left, bottom up. To get 2 types of Cisco models, you get bottom up Cisco and top down Cisco. So bottom up Cisco will be this one, left node, root node, left root, left, right. And that's what all the platforms agree on. Root, left, right. And this is a self-balancing tree you see in the board. So actually, if you think about R, we think about X. If my read is your right, we have a read, write, execution schema that has the following pattern: read, then write, then execute. Read, then write, then execute. Then we have read, write, then we have write, then execute, then read. Write, then execute, then read. Then we have the last one, execute, write, and then read. Execute, write, and then read. This is really the original computation. These are three matrices that you should never encode in the system for the system to execute in order of any order there is. So the matrix again will be R, W, X, W, R, X, and X, R, and X, W, R. Now, this table is a lookup table too, because you have a shared read mode, and a shared one read, three read, and one write. Stuff from read, you have an angular read. So you have 0, 0 as a read, 1, 1, and 2, 2 as a read. Via the lookup table, you can look up areas too. So if you only need an area of index 1 of x and then y, x and y, you don't need the other ones. So you get x, read, write, execute. You get x here. So execute means run this code, execution, execute, read, write. Which we have, as you see, we have R22. Not equal to R22 is read. And we have the command read. In the table of read. We have RW, you have read, then write, then execute. You have write, then read, then execute. It depends on what you need. But you can have execute. You can have execute. You can have execute and execute. We have this main one you get for the reading. So I'm going to use this one for reading and writing. And when you execute it, this is just a read one. So the writing one will be, if I want to write, then execute, I have to start from the right. So write, execute will be W, WR. W mean W. So if you have to read right, if you want to read right, execute. If you want to execute, so if you want to read before the execute, you want to form a read and a write. So two reads, one read and one write. This is one read. We don't have one read here. Now, so for one, you also have a write. So a write will be write, execute, read. So write, execute, read. Write, write, execute, read. Write, execute, read on the keyboards. Execute, write, and read. We have as you can see, I have considered matrix here. All I can see basically. So you get write, execute, and read. And you get read, write, and execute. But at the angles, we share a read and a write. At the diagonals, we have write. This writing means writing to some kind of system while it's operating. And you get read. Now, we have to have a Cisco model of the self-balancing tree that can give us read, and write. In this kind of framework of polarity as dimensions. Not as the values literally, but as the space for the view, as the space to do it. So we only want to have a RW, but we can have an X as well. So The X would be, let me just make the X as well, because that makes more sense. So the execution order will be, so if I'm reading and writing, this is two execution to one execution order. So this is two execution. So let me read the right execute. The execute will be execute, then read write, execute, execute then read, execute, write, then execute. Yes, that will execute then write, then read. If you also want to end with the reading or the writing, and that's the same work. So execute, read, and write. There'll be write and read, write or read, execute. Oh yeah, so basically the follow will be execute will be uh execute, execute, then write, then read, execute, then read. So execute, then write, then read, and then execute, then read, read, execute, um, read, execute, then write. And you have this. You read this one. Get this. You have the get X here. Read, write, then execute, then read. So we have three tables of consensus we can formalize now. Mathematically, this is basically the consensus matrix. So we have read, write, execute on the left, on the root. Left, again, we have write, read, and then execute on the left node of the string node. And because it's a tree, it's not T for tango, R for Romeo, I for indigo, E for echo. And X, you have to try to form a tree that's basically in parallel, and it's disjoint tree formed on the world. So, so the indexing will be isomorphic to some state of the system here in the read, but we should have the command to execute while the system is we should run. And this is basically where the bottom up parsing comes in. We try to determine how to rotate the tray, the Cisco tray, to have an execution order of something that's sent, some answer that's sent. And that system will be sent over the time of integral. So that's the problem there. So and how the problem will solve is basically a calculator. So we have write execute read, execute write read, and then read execute write for the writing first. And then we have execute write read execute write, and write execute write read execute. As you can see on the axes. So if these are axes, where does the trade come in? Where does the trade become interdependent of the execute? What do we need to have a shared consensus with tripolar systems? When do we agree on something can execute? Because if I'm reading right check, when we agree on execute is basically when we agree on the execute flag, what the execute flag is. And that how we do this is this. So we get axis of 1, 2, 3. R W X. X W X. Right, then read the right execute, read, write and execute, read. And then you have execute, write. Execute, write, and read. So the problem here is kind of problem of the execution order. So we need to find execute and map read to write. So the mapping will be how many reads make one write. So you have a lookup table now. So how many reads makes one write? So this is how it's going to work out. We have 2 reads to 2 reads. So we have a table here. So we have 2 reads two reads, two reads of RR, two outs, one write, two reads to make one read. And then two reads to make one write, to make one read. And one observation, one or two R. So it turns out that 1/2R is basically the equivalent of the read, and this will give you execution order. So this you have to have the system, the whole unit of the message state of the two read operations, which is one filter, one flash to send to execute the message. So for every two reads you have of a program state, tomographic state, that is equal to later time. Later please. Thank you. So for every two reads you have one write, one implicit write, one implicit one explicit write operation you can do. This explicit write is a reflection of the system, filter and flash sequences. So the filter represents the sorting of the system, but the flash is the sequence of sorting flash. So the flash will be the sending of the message, or the command and the control system. Like actually give you some food. So the one read, two read equals to one write with the frame goal reasons. We have a whole message sent. The whole message, if the very message is sent, that will be one whole unit of the message. This should be 256 one whole unit of the message will be 522 bytes over 2 seconds. And that will be 522 bytes over 2 seconds. 512 bytes over 2 seconds is 512 bytes of memory per two read operations, which is one execute operation. Two RR, two reads make a write, two writes make an execute. So two reads make one. All right, two reads. Yes, you take two reads and then equal to one write operation. Basically, two reads bottom, two reads at the bottom make one write. No, one read is a write, but two writes, two reads makes one operation. You see, the tree has to balance itself out, and that's what it's going. So 525 bytes of data is just a difficult byte of data per 2 seconds. So two reads would be 2R to one write. As you can see here, you get 1, 2. So you get write, execute, and read. And you get write, then read, execute, then read. You get 2 hops. So you get 2 hops from one hop from read to left, root, right. One hop from the one hop from the right node, which is read, one hop from the right node of the right node, which is one hop from the right node, which is read, to the left node, which is read, root left right, which is right, which one for the right to the left, and you get execution. So and you have from the execute flag, you have 2 hops. 2 hops. You get 2 hops. That'll be right, read as right, and then one left node. So you have 2 hops, 2 hops, 2 hops left, 2 hops left to execute, and those 2 hops have if I'm writing, depending on the state of tomographic state I am in, so if I am already executing, I need to do that. If I'm writing, if I'm reading something, if I'm in the state of reading, and I want to execute, I can do a filter, a read filter, a read flash. A read flash represents the idea of 1/2, 1/2, one of the few messages 512 bytes of data, and the flash will be the sending of the information. So that would be one hop right, one hop right to execute. But if I'm already reading, that would be one. If I'm already right, so one right node is reading. I have to have two hops to execute. One making a total of if I'm reading and I want to execute another platform system, and that would be the so one so more formally will be one hop one hop left, one hop left, and if I'm reading, and my last operation was execute, my last operation was an execute, and then if I'm reading, and my last operation was a write. So that would be two hops. Right. If my hop, it's a function. It's a function. So mathematically, this is the correct way to do it. So you have to have a filter and a flash. So the flash is the sending of the information of the execution order. The flash. So flash can be the organization of the system. So the flash will be one hop left and one hop left, two hops left maximum, two left hops, two left hops based on the current state of the system. Maximum two left hops, maximum, and one hop minimum. So one hop, one hop in the worst case, two hops in the worst case, and that worst case will be 2t for the two times the message will be sent to one space allocation. So if the message will say two times, the two times will be to one space will be 512 551 milliseconds, 51 milliseconds per 51 milliseconds plus 72 milliseconds of time. For each 4 bytes, I have 4 bytes have been allocated to memory. So for each 4 bytes of the allocated the system has to be allocated 4 bytes ahead of time, and that 4 bytes will be 500 to 512, 512 512 times 4. And that'll be 2048 bytes of data allocated in an order, in sequence order. So the two left hubs are not auxiliary hubs. They're meant to measure the full maximum in one full hub. They're meant to be split up, but they're sound as one execute. Because execute equals to some execute read and write execute operations that can be determined a state of tomographic step. So it's 512 times 4, which would be 2,448 bytes of data sent over a protocol of a hub of three hubs over the sequence of three hubs. So the maximum hubs you can have is two. Wait, one, two, one, two. Over two hubs. Over two hubs. Two hubs. You get two hubs. So you get two hubs. So you get two hubs. You get two hubs, which are two left hubs, not right hubs. Two left hubs. So you get the root left right. Two left hops to get to the root of execute. And these two left hop are how we can practice with the 512 bytes of message, which is 2048 bytes of messages over two hops, over two, divided by two hops. But these two hops are not hop. You don't have to do this hops. You have to just rotate your dimension. So you don't want to do the hops per se. You just have to switch the context. You have to do a context switch. So the context switching represents to the dimension of your. You don't have to do the hops per se. You don't have to. You just have to do one context switch, and the context switch is just the change of the trade. So if you're operating on read write execute trade, you just take the state of the trade. So read becomes your read becomes a write, and that write is one switch. So you have to have two hops. Instead of two hops, you have two rotations of the tree. So the tree, cell you have to rotate twice. So these are two hops. You just have two twice, which will give you the message, the same message, but which percentage of the message, but the two hubs is too much. But you can have a read if you just want to execute, you just have to change your view to execute. But execution is not implicit; it's explicitly stated as two hops, which is two rotations. So my read becomes your execute, and your execute becomes my right, my right, and my right and my read, and your read becomes my right, and my right becomes your execute, and vice versa. So the dimension of the system is preserved because the filter, which is the flasher, is sent because you just looked away and it's sent. You just change the angle of the message. You just change what was there. Yeah. So you can have the table again, which is two one or two R makes one two R two read one R. So one read operation is on the right, and you have one right, and you get one right and one left operation. One right, and you get one left. So you get read, execute. So you have a table of. Let me draw it here, so I don't mess it up. So let me draw it here. So you have two main tables of operation. You have read, read, execute, and then read, execute, then write. So if I have a read, I have a write, but that means the table will be R X R W W R no R X W RX. So the three messages, you have three messages. So you have around R X R, or you have read read. You have R write execute read, and you have two vectors of it. Get right, you get read read write read write read write write execute write execute write execute write execute read. I have execute write read execute write read, and then you have execute write read. So basically, that's the choice. So you see the table here, the top one. You get read, write, execute, read, execute, write, read, and then you have the last one, which is execute, write, read. You have read, write, execute. And then you have read, read, execute, right. So as you can see, the system of read, write, execute. Also, but you just need two access of it, and this access will be a read, write, execute, write, and execute, write, read. These are two. This is one matrix you need. One order you need. So this is one order, one matrix you need. So if you get right, you get execute. If you get execute, you get right. You get read, two reads. I can see that two reads at the bottom. At the bottom of this table here, so you get the order write then execute. Because you see, write then execute. With this table, this matrix here is a 2 point. You get true operation. This is the order. So the order is on the right. So the order is on the far right, and that's basically on the other. So you get write, execute, then execute, write, and then read, and read. So you have two reads at the bottom. You can see there's also two read or two write at the bottom, and that's what gives you one execution order in the framework of implicit execution order for every two tables you construct of that. So the next one will be right. We don't write. So you see, basically the matrix is 9 by 9, but you're taking the 3 by 3. You see, the matrix is 2 by 2, 3 by 3. But you're taking a two, making a you're making it. You can take a 3 by 2 matrix to make the message to have three. You can take a 2 by 3 matrix, which is the two rows, three columns. I'm gonna use them to transpose to send a message. Well, so you can make it to the you have 2 by 2 by 3 by 3 by 2 messages. You have to do a transpose of it. But the transpose of this message will be, let's try it. 2 by 3 will be read execute read, right? And you get write execute. And you say, so you have this is not making sense. And you get the determinant. So you have to come up with the determinant. So the determinant of this message will be if they're cube, if they're same, the determinant of this will be so you have to calculate one over a times b. So the determinant of this message will be this is not determinant. So this is transpose. This is not determinant. You need two matrices. You need two. So if you have the right operation, do this. So this is what I need. I need the right operation. The transpose. So the transpose of the right operation is what I need to get the determinant of. So the determinant will set the boundary, the dimension of operation of execution order. So I need to calculate the determinant, which is one over a times d times c times a times one over a times d times plus c plus b. So one divided by this kind of matrix. By calculating the matrix of determinants of two trident systems, you get the execution of system on the fly for controlling system or commanding something. For security is concerned, since the lunchtime, I'm gonna eat, so let me try to do it properly. So I have two reads here, so I need two writes as well. So two writes as well. So two writes would be two writes would be two writes would be two writes would be so go two reads here, two writes. So I just need two writes one matrix. Two writes at the bottom as one axis. So the axis of like x, y, z. So this one's at the bottom axis, z. So you get z. So you get two writes. So I'm trying to find two writes, one bottom axis. So what's my tree model? So we have so the problem. So you get if I start with the right, if I start with a read, I get read, write, execute. Write, execute. If I go to read, execute, I can start with the read, write, execute, or I can start with the read, execute, and write as a sequence. Read, execute, and write. So read, execute, write, real. Read, execute, write. Write, read, execute. But this is not complete. This is basically wrong. Two right. No. This is a wrong one. So I need the read, write, execute. So the read, write, execute would be read, write, execute. Write, execute, read. But I'm trying to find this now. Would be that's not the choice. So only for two execute is in one axis. I'm just fine. So basically, you can have axis of right anywhere you go, but I'm trying to have it on the bottom, because it doesn't matter the order. It just basically can be diagonal too, but this is singular what to do. So because I go down, so you get read, write, execute is as in array, and then you get the conjugate way, which is write, read, execute. And you get read, write, execute two. Right, so you get write, execute, read, and you get read, execute, and then write. Write, read, and then execute. Write, read, and execute. Read, write, execute. So read, write, execute, and then you get read, execute, and then write. But this is not the balance of no, this to balance itself out. With the axis on the bottom, so it's the XYZ, we have two operation that is sequences. So since I can't find, since I can't compute, use so we're gonna use index one one one. I mean 10. So the mission is 10 on the x-axis and 01 on the y-axis, and that will give me 01 and 01 on the x-axis as one right equation. So the right matrix is for one right is here 10 01, and the read matrix is if I start with write up, if I start with reading, if I so if I start with writing and I complete read operation here, if I start with reading, well, if I start with reading, and I have a write operation. So if I let's say if I so R sub right, R sub right is the matrix one comma zero, 0 comma 1, and the matrix right W right read, right complete read is wisdom, right sub read is uh, uh, um if I want to read option, you get a right read execute. You get 0 1 2 0 2 0 1 2 0 2. So the matrix we will go on the board now is computed as determine which of these two matrices step. So let me try to let's do the board here. 1 second, guys. Let me just move up. Oh, it's moving here. All right, so the terminal ratio is basically AD times BC, A times D. But I'm looking for 1 over the terminal. That will give me the baseline matrix. So I have to get the terminal. So the transpose will bring the frame matrix to 0 0. So the consensus works by sharing some information. So if I share the transpose, not the actual matrix, the transpose of the matrix. So if I share, if my what am I saying? What's my control? So very important now you understand this, guys. So very important. So you have R equal to R sub W equal to R sub W equal to 1 comma 0 and 0 comma 1, and R sub read equal to 0 comma 2 and 0 comma 2. So 1 comma 2 and 1 1 1. Not theta 1 comma 2 1. Let me check it out. So you get right 1 comma 2. So 1 comma 2 is basically where you find read operation in write systems. And this matrix represents the kind of system of homogeneity. Because homogeneity is there, basically, you get a read to write and write to read. So this one is share. So this share this operation there between homogeneity between and write. And this is because this matrix so I'm trying to give you, so for this to solve, I'm trying to give you the transpose of the matrix. So I have to calculate the transpose of this. Transpose of the read and write. So I put a T at the top here. So again, is read, write, transpose. The transpose will be read, write T, T R sub W is equal to everything blue. 1 becomes a 0, so this is here. So you get 0 1 1 0. And this matrix what it gives sense to we share. So we share a 0 and a 1. But we don't send this one we send. The right place will be right of T, right of right read transpose of right of read, right to read, right to read is 1 2 1 comma 2 0 comma 2. So I send the transpose of my matrix instead of the actual matrix to the system or to compute it dynamically. So you need to send it, by the way. So you send, so you get read write then read sub team and get transpose of text. So transpose will be 0 1. The transpose of read write will be 0 1, and that will be 1 0 0 1 1 0, which is the matrix of x 0 X, you get the transpose of the Y matrix will be 1, 2, 0, 2. 0, 2. And now you have to now compute the A times D, A times D plus B times C, 1 over the determinant of this matrix, multiplication of matrices. And the multiplication we use our calculator to do it, and the multiplication will be, so I have to write it down here somewhere. So I'm going to raise this on the left. I'm going to execute this on problem. So I'm going to raise it right. This is one, but it's not ready to be set. So let me just go. There's what is force on spin this and what down, what down. So you have the so you get the transpose. So the transpose mean A times C. So we get 0 times A times 0 times 2, where 2 is A times D of A times A is basically A, C, D. A times D will be 2 times 0, 2 times 0, which is A times D, A times D plus, other A times D, plus, so yeah, sorry. So plus other A times D. So you get 2 times 0 plus other A times D. You need other measures. So A times D is this. So 2 times 0 of the transpose matrix, you get 2 times 0 plus 1 times 2 plus 1 times 2 plus 1 times 2, and that will give you 2 times 0 is 0, 2. So AD is 2, 2, 2, 2, 2, 2. And then we get A times D plus B times C. No, plus B times C. A times C. A times C. Because I can just do one matrix. Let me just do one matrix. Let me just do transpose and tangent. So we get the transpose of the transpose. If I'm working with the transpose matrix, so we get 0 times 2 is 2. 2 1 times 2 is 2. So 2 times 2 is A times D is 2. We should transpose 2. A times D, comma, A times D, A times D plus B times C plus B times C. So 2 plus B times C. 2 plus 2 times 1 is this. We get 2. And you get A times D, which is A times Z again is 1 there. So 2 A times Z, this one. So basically A times Z, so times B was C. So this is B. B is 1. A times B times 1 times 0, B times D, 1 times 2 is 2, plus 2 times 2 times A times D plus B times C. 1 second. Please, further. Half the system. Yeah, so I was saying to you, this system. So you have 2 times 2. 2 times 2 is 4. 4, but you gotta have 4 back to number. So you have A times B times C times D. So then 2 plus 2 is 4. 4. So get, I'm gonna raise this and put 4 down. So you know, get 2 already. 2, 2. A times D plus B times C. A times D is 0. A times D is 2. 2 times 0 is 0. Plus 0 times 1. So you get 1 plus, 1 plus, you should get minus, 1 minus, A times D minus, and let's determine 1 minus what? 1. So you get 1 there, 1. 1, and you get 1. So you get A times D minus B plus C. Was it plus? I don't know. No, yes, it's minus. So something is minus. This is minus. I remember being minus. It's plus. Please correct me. Because it's minus. So H of D minus B plus C. Yes, it's minus. I'm pretty sure. So 1. You get H of D times B plus C, which is minus, and then that will be H of D. H of D. You get the for all this is you get 1, and then H of D. So if you go to B, 2 times D, 2 times 0 is 0. 0 times 0 plus 0 plus 1 times 0 plus 1 times 0 is 0 plus 1. 2 times 1 is 2 times B plus D, 2 plus 2. So this is 1, 2. 1, 2. Minus 2, so 2, that means 2. 1, 2, and then we get C, C, 0 times C times C times A times D. C times A is 1, 0 times 1 is 0. Then 0 plus 0 times D, A times D. A times D. D, C plus D. C times 0 times 0 is 0. And then 0 times D times C. Which is 1 times 1 times 2 is 2. So 2, and we have 1 more to do. D 2 times 1 is 2. 2 times 1 minus 2 times 1 minus 2 times 1 minus something called 2 times 1 minus A times D C A times D times B plus C. 2 minus 1. So 2. So you get 1, 2, 1, 2, 2, 2 for the matrix, and that's the consists of the share. They share the determinant over the system. So the matrix 1, 2 on the x1, x0, 1, x0, 0, x0, 0 is 1, x0, 1 is 2, x0, 2 is 2, 0, 1 is 0, y1 is 2, and the last one is 2. So you get the A, B, C, D is 1, 2, 3, 4. Oh, 2 vectors that are you need at the time. 2 vectors you need at the time as 1, 2. What are you looking at? Good. So you get the system here of system of linear equation. But this equation is here. What is intended? So it's not gonna filter on you, because this is just the transpose of this one. But I'm gonna try to calculate the transpose of this one here. So let me use a calculator. Let me use a calculator for it. Where's my calculator? My calculator for it will be. So we get the calculator will be. Let me write this on the board here. The calculator will be in green color. In green will be 8 times D is 3. 1 times 2 is 2. 2 plus 1 times 0. 2 minus 1 times 0 is 0. So this is 2. And you get you get 2 You get B, 0 times 0 is 0. 2 times 1 is 2. 2 times 2. So you get 2, so you get 0 times, which is B, B times D. Is 0 times 2 is 2. So 0 times 2 is 0 times 2 is 0. Plus minus it should be minus 2. This is minus. Should be minus 2 here. Minus 2 there, not 2. You know, minus 2 means the system is substantial. So you gotta keep the negative 1 happening. Minus 2, so you get 2, which is 2, 0 times 1 is 0. 0 minus 0 times 1 D A D B C minus B minus 0 times 0 times 1. 0 times 1 is BD. B 0 times 2. 0 times 2 is 0 times 2. Minus BC. Minus 2 times 2 times 0. So this will be 0 here. And this will be, this is the minus solution. Let me show you. So I'm moving the minus 2 there. I can calculate. Let's show. Get C will be 1 times 0 times 0 times 0 times 0 0. And then 0 times 0 is 0 times 0, 0 times 0 is 0. And then 0, and then that's written down. And then 0 times, so you get D, which is 1. 1 times C, 1 times, no wait, 0 times C times A, B times C, 0 times 2 is 0. So C to A, B, C, C to A, and then D to C. 1 should be 1. Should be 1 here. 1 here. You get last one, which is J. 1 times 0, 0. 0 times 1. 0 times 1. 0 and then A. 1 times 2. 1 times 2. 2. So you get 2. So the measures are 2, 1, 1. 2, 3. That's 1. So you get 1 here. So the measures will be for this one. I put minus 2 there because I'm not sure. So I have to come. So this is be for the transpose of this one. So now there's a relation between the transpose and the matrix itself. So you get this matrix. Written matrix is 0, 1, 1, 0, 0, 1. And the read right matrix, and the right matrix is 0, 2, 1, 2. And you get these two matrices here. You have 1, 0, 1, 0, which is basically 1, 0, 1, 0, 1, 2. Which is the what determines the share. This is the matrix the share. And you get the transpose has determinant 2, which is 1, 1, 2, 2, 2. Which I believe is so, but I don't believe negative 2 is right. I just want to do something. Yeah, so 1, 2, not negative 2. 1, 2, 1, 2, 2, 2. Now we can now operate safely on the matrices. And that this will be calculation of this system. So this matrix here is shared between the two. And this matrix this one is here. So here go the arrows here. They work together to solve the problem. But two matrices is basically 1 over. So you put a message. If you put the matrices over the matrix, this matrix will be there because it's basically determinant of matrix multiplication. So we actually calculate the determinant of the matrix multiplied, which will be determinant will be 1 over the determinant matrix for the matrix to be set. And that matrix is basically 512 bytes of data that will need this kind of matrix of read write and execution order to send something, to control and command something, which are what scripting interfaces do, the control and the command. So the CP is the control and command on the file system. But the training rules, the training rules apply here because they have a shared binary figure. So I can determine that the message over the segment of ADBC is like this. So, for example, if I'm working on the transpose, I can use the verifier. The verifier, if the message is sent, I can verify the message like this. So if the message is basically 512 bytes of data, 512 divided by AD times BC, and AD will be AD times BC will be the matrix there. So 512 bytes of data over along the axis of one along the axis of the terminal, which is one one plus three. Terms of things. So you get AD times BC minus BC, which is great. Over the measures of 512 divided by the measures of 1 on x-axis. We get the x-axis will be the x-axis will be 1 plus 1, which is 2, divided by 2, which was 512, 256 bytes used of data. We get 0 plus 2. No, sorry. So in the half term, so 512 back to data divided by 2, 1 plus 1, which is x-axis is 2, is divided by 2, is 1 times 1. You get 512 bytes of data divided by 2, which would be 256. Wait. No, so 512 bytes of data divided by 2 will give you 256 bytes of data, which is 1 plus 1. And this basically the x-axis 1, they have the half system. They're verifying, so for the system to work, they'll be verifying if they're using the normal matrix, the one that was the original matrix is 256 bytes of data at half time. So this proves that they have half verification. Because 2 is basically giving you this 256 bytes of data over the segments of the model. So 256 times 2 is 512. And you now have the other one, which is 512 divided by 2. Again, in the first matrix, which will be the read to write and the write to read matrix, we give you 200. So if the 250 bytes of data in the memory of the OB nexus message, OBI nexus, O for Oscar, B for Bravo, I for Indigo, N for number, E for Echo, X for X-ray, U for umbrella, and S for Sarah. So that would be basically this is 2 bytes to one system. They hold 2 memory, and then you have the half message. So the half message will be the determinant, and the determinant will work in 3. So you have x plus y. So you get 1 plus 3. 1 plus 2 is 3. Because you get 2 separate messages. 1 plus 2 is 3. And you get an extra message of 1, 2, and then 2, 2. So you get 1. So you get 512 divided by 2, which would be 512 divided by 3, which is 1 plus 2 is 3, which is 17, 117, 170,665, 170.67, 512 divided by 3 would give us 170.6 recurrent. 170.67 bytes recurrent. But they add up to plus 512. So you get again, so you have 170.66667 plus 512 divided by 4. 2 plus 2 is 4. Which will give you 296. So plus 290 plus 512 divided by plus 512 divided by 4. We should add up to the message of 200 2 plus 2. So basically the message basically we'll add this to some of the message which I got here. Right, but this basically I got it right here. 290, but the same one here. So I can be on my laptop here. So it will give you the other half of the message. Because the other half of the message, so this is about a half fast the message sends, which is basically the work done. There's potential work and there's potential to do energy, potential to send a message. Which like if you're like in the helicopter and you're gonna do a parachute, you have to put your energy to fall down, and you're gonna put you down. You're having a measurement of gravity, which is a muon, 1/100, would be 100. So you have 100 potential energy of someone on the floor to fall down, 10% stability factor to fall down. So the factor of 100 is as you rise up to the sky in helicopter, you're gonna jump. That's the potential energy of the work, and the work is basically work of the potential and work of the done, work potential and work done, which is the halfway of the potential, which is like a quarter of the energy you're gonna have to actually do in 25 in ratio of 100 divided by 100 divided by 4, which will be 25. So you have 25 units of energy in potential work, and you 25 units of energy in potential work. But the potential work has a ratio to 3 to so you have 3 to 4, 3 divided by 4 potential, and plus to 1/4 work done that you can act on to send a message, which is work times displacement of times work with force times displacement. The force on object and this how an object and the polar via theta, which is the rule of theta or angular momentum. Thank you guys. Angular momentum is what I said. Thank you for watching the video. Like, share, subscribe if you get the message. That's how NSIGII works, the Project for Human Rights. And if you know about basically using it to command and control something whilst it's flying. Doesn't matter the message, it doesn't matter the Python script, because NSIGII is polyglotic. So that means you can choose any language you want, but it's a scripting system. And it's not a full-blown programming language. It's a scripting system. So you can understand NSIGII as a scripting system. You can connect Python, C, any standard script to the system of a NSIGII, and the NSIGII will run that code for duty as a cron job. But it works because it's safe. It's safe to run. So the file format is N for November, S for Sarah, if echo expression files, and N for November, S for Sarah, N for November, I for Indigo, F for France. NSIGII intent files. Thank you for watching. Now I have to go and eat lunch.